Welcome. We have solved the diffusion equation analytically for certain boundary conditions, and we looked at two such methods of deriving analytical solution for the classical diffusion equation. Now we want to solve this equation numerically. Okay. So what does it involve when we have to solve this equation numerically is what I want to discuss next in this part of the lecture. So let us take the diffusion equation. So we have dou c by dou t, which is d del squared c by del x squared. This is the equation that we are trying to solve. When we solve numerically, there are two different ways in which this equation can be solved. One is using an approach known as finite difference approach. The other one is to use a spectral technique. Specifically, we will use Fourier spectral technique. So first I am going to use the finite difference technique to solve this equation. What does it involve in solving this equation using finite difference? Suppose I have the domain, this is the x domain. In finite difference technique, first we discretize the domain. Okay. And the discretization points, for example, this is 0, this is 1, this is 2, etc., up to it goes to n points. So each discrete part is del x, right? N times or n minus 1 times del x is basically the entire length. So this is del x, this is 2 del x, this is 3 del x, this is 4 del x, etc. So up to n, so it will have n del x as the total length. So you take the total length and you divide it into del x pieces. So you will have some n number of such pieces. So that is what we take for the spatial part. And I am going to refer to each one of these points that I have discretized by some I. Okay, I refers to any discretization point, any spatial discretization point. Of course, we also discretize it in time. So we also have the time axis, and we have 0 time, and then we have delta t time, and we have 2 delta t time, etc. So the solution at any given time at all these points that I have discretized, if I give, then I have given the solution. So this is the finite difference technique. For doing this, okay, so we are going to use the difference formula to approximate the derivatives. This difference formula are typically derived from Taylor series expansion that you might have seen. We will also do it as a tutorial in this course. So for example, dou c by dou t is approximated as follows. It is c at time t plus delta t minus c at time t divided by delta t. And remember, this is partial derivative. So I am differentiating c with respect to time. So I need to tell at what position. So I am going to do this at every ith position. Okay, C I t plus delta t minus C I at t by delta t is basically dou c by dou t at the ith position, right. So this is the discretization for the left hand side. Now how do we discretize for the right hand side? That is what we will do next, and for doing that, let us take d del squared c by del x squared is equal to d by delta x squared c w plus c e minus 2 c I, that by delta x squared is what is here. What is w and what is e? If you have ith position, the point to the west of it is CW, the point to the east of it is CE. Okay, so this is my notation. This is called the finite difference stencil, for example. Sometimes it is also written as CW is written as I minus 1, CE is written as I plus 1. Okay. And in 2 dimensions, if you are there, you will also have north south points, okay, because then the position indices themselves will run from I and j, because there is x and y axis. Then you will also have j minus 1 and j plus 1. Okay. So, that is what basically this is. So, we will come back to the 2D one later. We will first solve it in 1 dimension. So, this is the discretization for it. Now, because this is partial derivative with respect to x, we also need to tell at what time. There are 2 ways of doing it. The simplest way is to say that all these c's are taken at time t. Let us start with that. And now let us put them together. So, what do I have? C I t plus delta t minus C I t divided by delta t is equal to d by delta x squared, and then C I minus 1 t plus C I plus 1 t minus 2 C I t. Okay, so, let us get all the quantities which are at time t to the right hand side. So, I get the C I t plus delta t. So, at any ith position, if I want to know what is the composition at some future time t plus delta t, that is related to the quantity at time t as follows. So, C I t, I have to take the composition at that position in the previous time, and this delta t d delta t by delta x squared. So, I am going to call that as alpha minus 2 into CIT. So, I am going to get this is 1 minus 2 alpha, where alpha is equal to d delta t by delta x squared. Okay, please remember, whenever you do diffusion problems, you are always going to get this delta x squared by dt. Okay, x squared by dt, okay, d delta t by delta x squared. Okay. So, you are going to keep getting this quantity. Okay. So, CIT is coming from here, so that is 1, and there is minus 2 CIT, and that is multiplied by this quantity. So, minus 2 alpha CIT plus alpha times C I minus 1 t plus C I plus 1 t. So, in other words, what we are saying is that at any position I, if you want to know what is the composition in some future time delta t, you take the current one at that position multiply by 1 minus 2 alpha, where alpha is d delta t by del x squared, add to it alpha times to the left of that position and to the right of that position. So, this then will give you the solution. Now, you can see why I need initial condition. To kick start this algorithm, at some time t equal to 0, if I know all C i's, that is the initial condition. If I have that, using that I can get time delta t, and then I can put the delta t back here, because I know at time delta t I can get it at 2 delta t. Then I can put it back here, I know at 2 delta t, so I can get it at 3 delta t. So, in other words, you can march in time by taking the current value of composition at different positions. Using that, you can predict the future value of composition at different positions. So, initial condition is required and one initial condition is sufficient. Now, we also need 2 boundary conditions. Why are they needed? Okay. So, let us go to the position discretization and take a closer look at what the position discretization means. Okay. So, we said that suppose I have a domain, then I am going to discretize it like this, right. I is any position. Now, if I am in the interior, to the left of I and to the right of I. So, this is I minus 1 and this is I plus 1. This is what we called as west and this is what we called as east. There are always points. So, for the ith position, when you need I minus 1 and I plus 1 compositions at this current time, you have it. But if you look at this end point, there is no point to the west, and if you look at this right end point, there is no point to the east. So, to determine for the end positions when you are at 0 or when you are at n, you have to determine what is CW for when I equal to 0. If I equal to 0, what is CW? If I equal to n, what is C east? These two questions we have to determine. For that we need two conditions. These are the two boundary conditions. Okay. If I give you two conditions, using those two conditions you will determine what CWCE is, CW for I equal to 0 case and CE for I equal to n case. So, you need, in addition to the initial condition, two boundary conditions to solve this set of equations. Now, what are the type of boundary conditions? This is not something that we discussed earlier, but it is important to have that discussion here. There are three different types of boundary conditions. Actually, there is four, one more we will look at later. One is called Dirichlet. In the case of Dirichlet, at I equal to 0 or I equal to n, you give the composition value itself, C is equal to some C naught. This is Dirichlet. There is a boundary condition that you can give, which is known as Neumann, in which case at I equal to 0 or I equal to n, you give dou C by dou x is equal to some alpha, dou C by dou x equal to some alpha. There is also a boundary condition which is known as a Robin, which is basically a linear combination of Dirichlet plus Neumann. Okay, Dirichlet plus Neumann. But at any position, for example, at I equal to 0, either you can specify this or you can specify this or you can specify this. You cannot specify more than one. You can't say at this position the composition is C naught and the dou C by dou x, which is nothing but the flux. In the case of temperature, dou T by dou x is basically the heat flux. In the case of diffusion equation, this is the mass flux. You can't prescribe both the concentration and flux at the same point. Okay. So, either you specify this or you specify that. Okay. Similarly, here also either you specify this or you specify that. Okay. So, this is something like in mechanics problems you would have seen. Suppose if I have a rod which is fixed to a wall, for example, it cannot have any displacements, then it will start developing stresses. If you want to keep it free of stresses, for example, one end, then it might start having displacements. But I cannot specify both that displacement is 0 and the stress should also be so much, that I cannot say. So, okay, the loading conditions are going to determine what the stress is going to be if I am going to constrain the position not to change, right. I am going to fix this rod at this point, then depending on loading condition it will develop stresses at this point. Similarly, if I say that I am going to leave this end of the rod free, then depending on loading conditions it will develop displacements. You can't say this is free, all the same it should also have only so much of displacement, that we do not have. Depending on the loading condition, the system will automatically choose. Similar thing is happening here also. You either give Dirichlet or Neumann, you do not specify both at the same point. You can specify Dirichlet at one point and Neumann at the other point, which is very commonly done. Okay. But you cannot specify at the same point both Dirichlet and Neumann. Okay. The only way you do both at the same point is by using Robin boundary condition, which is a linear combination of the two. But again, if you specified this, you do not have any control over this. So, the overall boundary condition is what is specified. There is one more boundary condition which is known as the periodic boundary condition, which is very important when we look at the spectral problem. So, I am not going to discuss periodic boundary condition in this case, but I want to talk about one more issue, namely that when we did the partial derivative of the composition with respect to position, we assumed that all of it was done at time t. There is nothing that stops you from doing it at some t plus delta t. Okay. The way we have done, by taking all the quantities on the right hand side of the equation, right here, by taking the del squared c by del x squared, when I took the partial derivative, I assumed that the time is fixed at the current time t. This is known as explicit method. Okay, explicit because it is given at this point and then I can calculate. But there is another way of doing it, so I do not have to specify the partial derivative at time t, but instead I can do at time t plus delta t, right. All the partial derivative says that the time has to be kept a constant, but it does not say that it has to be kept at the current time or at the future time. So you have the freedom to choose it at future time, which is what we do, and that is known as implicit method. In that case, the partial derivative of composition with respect to position is given as follows. So we say d del squared c by del x squared is equal to d by del x squared c west t plus delta t plus c east t plus delta t minus 2 c I t plus delta t. So, everything is at time t plus delta t, all right. So, now we have this. So, let us go back and try to find out what happens in this case. So, we have c I t plus delta t minus c I t divided by delta t equal to d by delta x squared, and then everything c west at t plus delta t plus c east at t plus delta t minus 2 c I t plus delta t. And you can pull all the t plus delta t terms to the left, and you can push all the t quantities to the right. So, you get what? C I t plus delta t into 1 plus 2 alpha, right, d delta t del x squared times 2, and this we defined as alpha. So, 2 alpha minus sign, so it comes here, it becomes 1 plus 2 alpha plus alpha times c west t plus delta t plus c east t plus delta t is equal to c I t, right. Now, there is a shorthand way of writing this. So, we write it like a matrix equation. So, let me say that c at 0 t plus delta t, c at position 1 t plus delta t, etcetera, c at n t plus delta t is equal to c 0 t, c 1 t, etcetera, up to c n t. Now, again the initial condition is known. So, at every position 0, 1, 2, 3 up to n, you will know what is the composition at time t. What you are trying to calculate it is the c at position 0, 1, 2, etcetera, at some future time t plus delta t. And if you look at some ith position, so it will become 1 plus 2 alpha, 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 right. For the next position I plus 1th position, it will become alpha, 1 plus 2 alpha, alpha, etcetera, except for these 2 points. Again, when you have this position, so this is 1 plus 2 alpha and alpha, there is nothing to the left of it. So, you need to use the boundary condition to determine what it is. Sometimes it will come here if it is periodic boundary condition, or sometimes it will get added to one of these terms if you have Neumann boundary condition. And if you have Dirichlet, you will not even consider this variable, because if this is fixed, for example, C0 is fixed for all times, then that does not have to be part of this solution matrix at all. Similarly, for this point, Cnth point also. Okay. So, this is where we need the 2 boundary conditions. This is where the initial condition is there, and you can solve this. Now, this is solving a set of algebraic equations using matrix method. So, you must have seen some things like Gauss-Jordan or Gaussian elimination or Gauss-Seidel or some such technique. You can use to invert this matrix and left multiply it to this solution, you will get this. and if this is like alpha and 1 plus 2 alpha and terms like that. So, that is a constant matrix. So, once you have inverted, you can keep multiplying it and keep getting the solution. There are advantages to using this method, even though it is costly in terms of inverting a matrix and getting the solution. On the other hand, the explicit method that we looked at is very trivial to implement, because it is just a set of algebraic equations, right. C I at some time t plus delta t is just some algebraic expression involving C i's at some time t. So, you can write it, you can just keep on doing it and you will keep getting the future solution. So, it is far more easier to implement, but in terms of what is known as stability, it has problems. So, we will discuss what these stability and accuracy issues are and why and how we deal with them. Okay. So, we will do that in the next lecture when we start actually solving these problems on the computer. Thank you.